Gadi, welcome. Good to see you. Thanks for joining us.
I'm very happy to be here. Thanks for having me. It's super exciting. And I think Susanna spoke about a lot of things already. So
yes,
Yes.
that was a great conversation. Yeah,
Happy to dive in as deep as you want, guys, on the infrastructure.
Ooh, okay. So you're inviting all the questions in the chat. Hey,
Yeah.
chat, if you have questions, go ahead and throw them in there.
Challenge accepted.
A couple thousand people watching you right now. You're gonna get some questions. Cool. So what are we talking about today, and why is it important for our customers?
Yeah, so yesterday we were super excited to announce our new instance types. Like Suzanne said, Inferentia 2 is our second generation inference optimized for generative AI applications, and TRN, another Tranium instance, TRN1N, which complements our Tranium-based instances with really high network bandwidth, 1600 gigabits per second, which is 4x as compared to other accelerated compute infrastructure that we have on AWS. So really giving customers that are training these large models and are bottlenecked on networking with super fast infrastructure and cost-effective infrastructure to run their training. So that's the base of the announcement. There is a very large team behind it that is doing the silicon design, the board design, the neuron software. This is our SDK that plugs in and enables that infrastructure for customers. So really a large celebration yesterday in the engineering group. What we are trying to do though with those instances is make sure that although the hardware is super complex, and I can show you some examples of the hardware here, I couldn't bring the entire server, it's fairly big, but at least pieces of it. I was with a startup company that we're working with earlier this week, and I was speaking to a few folks there, and someone was passing by and they were telling her, "Hey, this is Gadi from AWS. We're talking about hardware," and her feedback was the most amazing feedback I've ever seen. It was hardware. And why I like that feedback so much is because that's exactly the sentiment from data scientists. They don't want to understand the complexity of the hardware, and the hardware is super complex, and we can talk about it a bit. But they want an easy way to get that performance on the other hand. So the hardware has to be there. It also has to be really easy to use.
Yeah. So before we dive into like the performance and efficiency improvements in the chips, can we talk a little bit about why are there two chips? Why Tranium and why Inferentia?
Yeah, I was wondering about that.
Yeah, perfect question. So first of all, we started with inference only back 5 years ago. Most of the usage was in the cloud was inference. The models back then were, the largest model was something called BERT Large. This was 345 million parameters. We measured model sizes by the number of parameters in the model, and it was enough to build smaller chips that consume less power, but can give great results for those types of models. As the science improves, and like I think either Aaron and Steve, you mentioned that machine learning is moving so fast. As science improves, scientists are doing two things. First, are trying to invent new methodologies. The latest invention was back in 2017. So far that is the transformer. Attention is all you need paper that came out. That's kind of what is generating most of the generative AI applications we see today. That's kind of the underlying technology. And the other area where innovation happens is the size of the models. As the model turns out with linear algebra, the more math you do, the more accurate the results are. So we see huge
linear algebra.
So we see huge explosion in the model size. So going back from 2018, I mentioned the 300 million size. We are now talking 300 billion, trillion. You see all sorts of crazy numbers out there, and these models are becoming very challenging to deploy in the infrastructure because you can't do it with a single CPU or accelerator. You have to really build supercomputers, which is exactly what we did. We designed a machine learning processor that is purposely built for doing these complex computations. And we are building the machines and the infrastructure with networking, with our EFA, and of course data center scale to really build a supercomputer that is dedicated for machine learning processing.
Wow.
Yep.
Yeah,
So
exactly. So one thing that I heard was like hundreds and billions of processing power. Is that right?
that's the size of the model. So maybe just to kind of show you guys what I mean. So this is the Inferentia chip.
It looks so small.
It is small. I have a big hand.
Model on there.
I have a relatively big hand, but this is kind of the size as compared
Yeah.
to up to a 10.
Yeah.
And this is our friend Tranium.
Oh.
Is you can see almost 4x this.
Yeah.
Wow.
Now the train, each one of this Tranium sits on a card. This is the card,
Right.
and this fits here basically.
Okay.
And we have 16 of those inside the server. So they sit inside the server. We have 16 of them. Each one of them is coming with a fairly large heatsink. I couldn't hold it with my hand. It's pretty heavy if I had the heatsink here. And that's one Tranium server. And now we have thousands of those inside the data center to build the ultra cluster. And that's basically the supercomputer machine learning infrastructure I was talking about.
Got
So
it. I see a question in the chat that is.
I was going to say, so Tranium is, sorry, you could have carried on, but so Tranium is really targeted at training the models, right? Then I guess the clue's in the name, which is that where the bulk of the costs are in machine learning?
Yeah, so that's where we are seeing the industry kind of shaping up to in a very interesting way. Yes, to build these generative AI foundational models, especially if you are at the billions in the model size. In order to get them into an accurate place, you need to train also on terabytes of data. So it's not something you complete in a day. It's something that takes weeks and sometimes months, depends on the size of the model. And yes, the expenditure on these models is measured in millions of dollars. So the reason we've built Tranium is to help customers save on costs, still have the performance, actually exceed the performance in many cases of previous infrastructure that we deployed with other accelerators, but really keep costs under control. So with Tranium, customers can get up to 50% lower cost to train. So if you take a model, if you run it with Tranium, you basically can save up to half of your dollars. And this enables customers to do two things. First, they can either use those funds to do more models or to do other things with that will get their customers better applications, or they can train bigger models now for the same amount of dollars, and then get, like I mentioned before, high accuracy and basically better results for their applications.
Aaron, you're gonna ask a question before I spoke over you. My apologies.
No, it's okay. It's the internet latency. It's been happening all day, so I'm just going to go ahead and point the finger there. So my question's actually coming from the chat because, Gada, you're showing us the processors and the chips and everything, and one person asked, I'm getting distracted by this other one. They said, what if all 4 people of these are just AI? No, we're not AI. Okay, it's real. We're a real person. But the question said, are these chips available for purchase?
Yeah, so we are selling those chips. We are selling them as, for customers, it looks like a software in the cloud, and you get access to that on demand, and you have elasticity to use up to 30,000 of them under one networking. So it's really basically, like I said, a supercomputer, an HPC supercomputer that gives you that access. That's the way we engage with customers, and that's actually the best way to do it because these machines are not easy to build. If it was easy, everybody would do it. And they cost a lot. So the fact that we're giving a fraction, basically a time modulation on those supercomputers, that's huge advantage for customers that need the scale, need the elasticity, because you don't you train and then you find into your application, then you deploy the application for inference, and maybe in a few months you'll train again. So it's that elasticity helps customers really move really quickly. So we are focused on that.
So awesome. Thanks for answering the question directly from the chat. So I see a follow-up about the whole AI and whether or not we're AI, and that's what an AI would say. I agree with that.
Yeah.
You also talked about cost savings. So what are some of the innovations that help with performance and energy efficiency with cost savings?
Oh yeah. So we in the data center, as much as compute you can put inside the rack, the better the cost structure of that compute solution will be. So the chips we're building, because they're purposely built for machine, like I mentioned before, they are basically a machine learning processor that we purposely built for that purpose and that purpose only. They do that really well. So if they do that efficiently, it means that I can pack more performance for the power that I have inside the data center, and that allows me to give customers something that is, like I mentioned, up to 50% lower cost to train. And of course, the fact that we're building these systems in-house, chips, boards, servers, network, the entire the data center, all of that is happening inside AWS, gives us full control on the supply chain. And especially these days, super important to have that, because our customers demand very large clusters, and our ability to scale and build those data centers fast enough is really critical to make sure that they can continue innovate for their customers. So that's the main reason why we are so efficient in what we do.
So I understand that you had some graphics to show us that kind of illustrate these points.
Yeah. So let's jump this on screen. I can. So we launched, like I mentioned, we launched Inf2 yesterday.
Yeah.
We have one partner. We have a few partners, but one of them is Runway. Runway is a startup that Suzanne mentioned. I think there was a question on what are the use cases for generative AI. So Runway is a great example of a company that is running really quickly and providing basically what they call it magic tools to be able to generate images in images and scenes and 3D scenes and audio in ways that were not possible before. Simple text that generates that. So Runway sees up to 2x higher throughput for some of the models with Inferentia 2. And again, in the words of the CEO, it enables them to introduce more features to their customers, like I mentioned before. But let's jump to a demo. We have here, I did it in a video simply because there's a lot of things going on the screen here, and I just can't type and talk at the same time. But if you can do play and pause at the same time. So
it's like trying to walk and chew gum at the same time.
Yeah. But could an AI do it any better?
Ooh, I don't know. Chat, what do you think? Let us know.
So what we have here on screen, on the left-hand side, is basically a Jupyter notebook. This is what developers will use to test a model, and we are now running on an Inf2 instance. On the right-hand side, you see at the top two. I'm hoping it's coming through well on the video. You can see two bars here at the top. Each one of them is a processor we call neuron core. We have two of them inside each Inferentia 2 chip, and right now they're idle. Nothing is happening. We already generated an image here, but let's see how this thing happens live. So we are adding the input here on the top, on the prompt.
So our input is asking for it to generate an image based on some contextual text?
Correct, and it happened already so quickly.
Wow.
We have a new image. So this is a new image. Basically, the prompt was a beautiful modern house in New York, award-winning photography with grass and interior. So that's basically a picture from the interior with grass and showing you what's supposed to be a house in New York. So that's and all of that happened in 2.75 seconds for that image, for that specific image. And
that's
what happened?
Quick, yeah.
What happens behind the scenes is that there are actually 50 samples, 50, of the same image, and then of course one image is being picked as the best image. It's called 50 steps in the Stable Diffusion world. This is a model called Stable Diffusion 2.1 that came from Stability AI and resides on Hugging Face. Hugging Face is well known in the industry as kind of the de facto repository for machine learning models. So we just took the open source model from Hugging Face. We deployed it on Inf2, no change to the model. It's all running in PyTorch, which is a popular machine learning framework. And like I mentioned in the beginning, if you remember, the data scientist that said
hardware.
On the hardware, that's exactly what we are aiming to do. We are not asking our customers to change their models, change their applications. It's all running through standard frameworks like PyTorch and TensorFlow. We're working now on JAX. JAX will come later this year. And the entire goal here is to hide all the complexity from customers and enable them to run as fast as they can, as cost effectively as they can. So let's try another image, and it runs really quick. But if the viewers can look here on the side on the neural cores, we'll have another prompt, and then you can see the cores running for.
Oh yeah, I can just see this like changing the blue shading. Yeah.
Yep. And then we have another image. Of course, this is a development environment, so everything happens one at a time.
Right.
But if you run it as with an inference server, you can hammer the hardware and make sure utilization is 100% all the time, and that way every second or so you'll get a new image if it's a service that you are enabling for your customers. And here was another one, again, kind of 2.770, and this is another architectural structure that we asked the model to do. But the sky's the limit. There's a whole new space called prompt engineering. I'm sure you guys are aware, where it might become a new profession. I think maybe taught somewhere on how to optimize the input that goes into these models to make sure you get the best output.
Yeah, I can imagine this is pretty powerful for like architects to kind of craft some ideas. Or maybe someone who's doing a landscape architecture, or someone who wants to create a photo of themselves wearing armor. I have no idea. Use cases are kind of endless.
Yes, on the image side, use case, anything that is image will be for sure. My prediction for sure will be impacted by this. All the heavy lifting, non-creative work that needs to happen can happen with these models, and of course, humans will kind of direct the model what to do in terms of prompt engineering, like I mentioned. But really, it's like Suzanne mentioned, it's a productivity tool that our customers are the startups and the enterprises that we work with see a lot of potential in, and we are just enabling the best hardware for the task.
So we talked earlier about the cost efficiencies, right?
Yes.
And you were showing us the examples of the chips. So I'm kind of curious to dive into those chips themselves. I mean, what are the innovations in those chips that are helping drive this? I don't think we've touched on it so far in this session.
We haven't. So the chips. Maybe I'll bring this back again. The chip has two main components. One, it's very hard. I don't know if it's easy to see. Let me know. So you can see a big rectangle.
Yeah.
Yeah. You can see two smaller
ones. Yeah.
Small ones. So the big one is where we are designing all of the compute. All of the compute happens there. We have dedicated engines to run what I think I mentioned before, linear algebra. And Steve, you were not. That's what
it took me right back to my school days. Like, oh no.
But it's basically large engines that do matrix multiplications. That's the linear algebra part, and they do that very performantly. In order to feed those, and that's where the parameters are loaded. But in order to feed those engines and make sure they're busy all the time, we also need very fast memory. So those are the two smaller chunks you saw there. Those are HBM memories. For example, on the Inferentia chip, the memory bandwidth we have inside the server is 9.8 terabytes. So just to put this in perspective, consumer SSD is like half a terabyte. So think 20 consumer SSDs. Every second, I can read all of the content from those 20 SSDs every second on a single chip. Okay?
Wow.
Just to give you the scale of how fast this thing works. And what this means, especially for generative AI inference, memory bandwidth is critical because you like I mentioned before in the case of the stable diffusion model, you need to run the image 50 times. Run compute and generate 50 images in order to select the best one. Memory bandwidth is critical in this. Of course, you need high compute, but you also need fast memory, so the compute will not be idle waiting for data to come. So we invested really a lot in the compute, just making sure it's very beefy compared to Inferentia 1, the first chip we had, if you remember. We are 3x the compute in Inferentia 2, and the memory and the latency is 10x lower in terms of what customers see as the end-to-end result at the end. And this is again to enable highly performant generative AI applications like image, like speech. Customers today, we have customers doing speech. Alexa is one of them. Amazon Alexa, all of Amazon Alexa speech generation is all the utterance coming back to customers are generated by on Inferentia. So you can think of it also as generative. There is no, it basically generates voice from text. So that's also, I would at least define it as generative AI, and that's 100%. All of Alexa is 100% on Inferentia.
There's a great question came in on chat. Actually, I'm guessing that somebody is thinking about building one of these, but does it require a special motherboard? You showed briefly a piece of a motherboard earlier on, but I imagine it does, right?
This is all in-house designed. Yeah, I can. Sadly, Dave, I apologize. I cannot ship it to your home, and you can. There's actually no PCA connection here, also, so you cannot plug it into your PC. Apologies.
Yeah, I guess the gaming PC are looking at this thinking, "Oh, I'll have one of those under my desk."
all the gamers.
Yeah.
Yep.
So you mentioned more throughput and lower latency at a reduced cost.
Yep. Reduced cost is very important. So again, let's start with training. I need to probably kill this. Yes. Okay, so with Tranium, again, I mentioned before we are up to 50%. Here is a case where actually 72% lower costs. This is an encoder only, a BERT class model. But we kind of, the 50 is kind of an average across the board. So it's really dependent on the model. But in this case, when customers run, this is a cluster of 16 Traniums. So think 16 of those chips times 16. Okay. How many? This is how many you have. 256 of those running in concert, and hammering on training that encoder model. So comparing to a GPU cluster on AWS, this was 2.3x faster. It was almost half the energy, 47%, and the cost was 72% lower.
It's half the energy because it's processing faster, so it doesn't have to spend as much time processing, right?
It's processing faster, and therefore we use less. We need to use less watts. Correct. Across the training job. Correct. Similar benefits we see on the same model with when we serve that model with Inferentia 2. So we actually need half the number of instances because we are 2x the performance in that case, and then it's half the energy as a result, and the cost is significantly lower, 65% lower cost. But this is kind of a small model. Let's talk generative AI models. So this is inferencing a model called OPT. OPT is a GPT style, so ChatGPT-like style model that came out of Meta Research, and it's open source, so we could take it. So this is an example on the left side. This is an example with a 30 billion size model, inferencing 30 billion size model on Inferentia 2 server. And you can see that the throughput, we are 65% high throughput when we look at comparable.
Can I just go into when you say 30 billion, are you talking about parameter size there?
Parameter size, yes.
Okay.
And we are measuring it with tokens per second. So how many characters can come out per second? So you can see 600, almost 620 on Inferentia as compared to 360, 70, let's say, call it, on the comparable inference optimized instance. The cost is again more than half the cost, and then when we go to a larger model, we actually get out of memory on the accelerated compute instances, and that's the result of how much memory we packed inside the server. This model is actually larger than what the server allows, so you get out of memory when you try on different servers. And similar benefits we see also on the computer vision side. This is a preview of what's coming in the next release in our software. It's not available today, but that's measurements we are doing internally now. And you can see different types of models. There is a clip model, which is generative model, multimodality actually, with text and image. You can see 86% lower cost, and then stable diffusion is 50%. That's the demo I showed before. That's 50% lower cost. And vision transformers, this is taking the same transformers that do the text generation and actually applying them to images. These type of models called vision transformers, and we are at almost half the cost, 51%. And again, important to say that all of these models, from a developer and ease of use, we are taking open source models. We are not modifying them to squeeze performance. We are not adapting them to the hardware. There's all of this complexity is hidden by our SDK. We have a compiler we call Neuron, and this is where we are stripping away complexity from customers and investing heavily in compiler technology to make sure that these models run efficiently on top of our hardware.
Yeah, I'm glad you just mentioned SDK, because earlier on you were talking about data scientists, right, and infrastructure, and right, response, right? But what about developers, right? How easy is it for them to get on board and get started with these instances? What have we done to make it easy there?
Yeah, perfect question. So, from a developer perspective, they need to install our Neuron SDK. It's basically a plugin into popular frameworks like PyTorch and TensorFlow. And so from a customer developer experience, it looks and behaves the same. Let me show you some code examples. This is training from Hugging Face a model. And what you have here on screen is basically you are calling the trainer wrapper, which is trainer is an API from Hugging Face. So you just need to make sure that this line of code points to our hardware. That's it. No other change. So one line of code change. If you want to bring this is from a Hugging Face trainer-based models. This is the API. If you want to bring your own model, fine, no problem. The previous slide I didn't mention it. We are partnering up with the open source community and companies like Meta, Google, Apple into an open source project called OpenXLA. XLA is basically a compiler technology that all of these companies and open source developers are developing, including Amazon, to make sure that we have one interface one common interface to lower these models into the hardware. So what you see here is a PyTorch implementation of that XLA. So it's within PyTorch. Again, it's standard PyTorch. Nothing specific for training, which this is all standard XLA bits that customers are using. So that's on the training side, and on the inference side, it's exactly the same thing. The PyTorch support, you need to import the first line. You import the Neuron SDK, and then you call a trace function, which basically tells the framework to lower that model into Inferentia. That's it.
This is all done through Neuron?
This is all done through Neuron behind the scenes. Again, we are using standard APIs from PyTorch.
And Steve was asking about developers and the impact of developers. So I'm guessing this might integrate with other services as well.
Yes, these instances are EC2 instances, so they come with all of the regular bits and services that customers are used to get with AWS. So it's container services like ECS, EKS. It's FSX for Lustre. If you are doing large amounts of data streaming into your training cluster, FSX is the fastest probably. Or S3, you can use S3 as well. SageMaker, of course, super easy for customers to take the SageMaker models and instead of pointing to CPU or to other accelerated compute, they can point them to Inferentia or Tranium, depends if they're training or running inference. Fully supported by SageMaker. So really, again, going back to the experience and to that comment on hardware at the beginning, we are trying to make sure that for customers it looks, feels, and behaves like any other piece of software, and all the hardware complexity is being stripped away.
Yeah, I think that goes back to what Suzanne was saying in the previous segment, right? It's take what you know and just use this.
Correct.
Right, without significant like relearning or whatever that you need to do.
Speaking of learning, so everyone is watching us. Where do they go to start learning more about this and get started?
So getting started is easy. Like I said, if you know PyTorch and if you know TensorFlow, and we have JAX coming up later this year, then you are 95% good to go. There is an SDK, the link here, the QR code. You can just go into our documentation and get started. We have sample tutorials, sample codes, tutorials, and of course detailed documentation if you really want to geek out on how to optimize server. But out of the box, most customers see great performance like we discussed before.
Perfect.
This is great.
Yeah, thank you.
Gadi, thank you so much for being here. Thanks for talking about Tranium and Inf2 and all the power behind it, and hardware.
And he mentioned linear algebra twice. Ooh.
but tell us how you really feel about hardware.
I'm very excited with hardware, but I'm not sure the average data scientist shares that. But I think this is what we see already. It's kind of fueling the innovation with large customers and small startups, because both today want to save on cost, especially in the atmosphere today in the industry. So cost is super important. Saving on power is super important. We want to make sure we minimize the impact on what we do. And the performance is super important because customers want to get to results really quickly and advance the ML science. Like Steve mentioned before, it's moving fast. It's continuing to move faster. Guys, super glad to be here. Thank you for inviting me. And
thanks for coming on.
Next time.
Thanks for being here.